Alright, today we're going to take all the trig identities we learned last time, and we're going to put them to use by simplifying complicated trig expressions. In actuality, they won't be that complicated, but this is an important skill in calculus, so we're just going to be practicing that today. You will eventually want your trig identities to be memorized, just because it'll be easier to simplify things and work with trig expressions if you have these on hand, versus having to look them up every time. So this is a good opportunity to just pause the video and see how many of these you remember, and then check what you remember against what I have. So here's all the trig identities that we currently know, and there are more of them, which is another reason why it's important to memorize these ones. The rest of this video is just going to be 19 examples of simplifying trig expressions. With some of these, you might be able to figure them out faster on your own rather than listening to me explain them, and you're welcome to do that, just check your work against what I write. But the only way to get better at these problems is to just do a lot of them. And the more examples you see, the more you'll start to find common tricks and approaches to these problems. So just follow along as I explain how to simplify all 19 of these examples. In number 1, I'm going to use the fact that secant is actually 1 over cosine of theta. Because then if I multiply that by cosine of theta, you could think of this as being over 1, then the cosines would just cancel out and I'm just left with 1 as my answer. So in this example, I used the reciprocal identity. In number 2, I noticed that we have tangent squared and secant squared. And when you have trig functions being squared, you should always look in the Pythagorean identities first. Now there isn't one in here that says exactly what we want, because we're looking for tangent squared minus secant squared. But I notice here I have something that says tangent squared equals secant squared minus 1. So I'm just going to replace the tangent squared in the problem with secant squared minus 1. So we'll put that here, and then we still have minus secant squared. So these parentheses don't really mean anything. And so we have secant squared minus secant squared, those go away, and we're left with just negative 1. So in this example I used a Pythagorean identity. And for number 3, I'm going to use an even and odd identity because I have sine of negative theta. And I remember that that's the same as negative sine of theta. But on the bottom, cosine was even, so cosine of negative theta, the negative just disappears and we're left with cosine of theta. Now if you think of just taking this negative out front, we'd have negative and then sine of theta over cosine of theta. And I can take this farther because sine over cosine is tangent. So this is the same thing as just negative tangent of theta. And that's as far as I'm going to take it. So again, that example required the even and odd identities. Number 4 might seem a little unfair because we have to use natural log, so you're going to have to remember your log properties. So I have natural log of, and then absolute value of cotangent. So I'm just going to take a quick sidestep and explain the reason we have absolute values here is because cotangent can technically spit out negative values. Like if you think of the graph of cotangent, it looked like this. So there were negative output values, and you can't take the log of a negative number. So they just put absolute value bars there just to fix the problem, basically. So back to actually simplifying this, we have natural log of this and then natural log of this. We've got two different terms, and they're being added together. So you have to remember that if you're adding two logs together, you can combine them into one log term and multiply the inputs. So I'll write natural log of, and then I'm going to keep the absolute value bars just in case we have negative numbers inside, and then it would be cotangent of theta times, and then this stuff, 1 plus tangent squared of theta. So now we just have one log term, but the inside is kind of a mess, so let's see what we can do with that. Again, we have 1 plus tangent squared, and that seems a lot like a Pythagorean identity. Matter of fact, 1 plus tangent squared is the same thing as secant squared. So I'll rewrite this as natural log of cotangent of theta times, and then I'll just change this to secant squared of theta. And we might be able to go farther with this because we still have two different trig functions. Let's see if we can take this farther. So I'm going to think of cotangent, I'm going to break this up into its pieces. So I'm going to think of cotangent as cosine of theta over sine of theta, because secant is the same as 1 over cosine. So secant squared is 1 over cosine squared of theta. And now we see that we've got a cosine on top and a couple cosines on bottom here, so we can cancel one of those out. So that would leave me with 1 over sine of theta times 1 over cosine of theta. Now there's nothing really to do to combine these, but I could change this back into cosecant and change this into secant. So the final answer will be the natural log of cosecant of theta times secant of theta. So this problem required us to use the Pythagorean identities, the reciprocal identities, and we had to know a little bit about our log properties. In number 5, we have secant to the 4th and tangent to the 4th. And that's a little weird because the Pythagorean identities only have things raised to the 2nd power. So the first thing I'm going to do is actually factor this, because even though these are the 4th powers, they're both also technically perfect squares. So if you think of this as secant squared of x minus tangent squared of x, and then secant squared plus tangent squared, this factors as a difference of squares. And now we have a whole bunch of squared functions, so let's check the Pythagorean identities again. So I see we have a secant squared minus tangent squared, so I can replace that with a 1. So now I just have 1 times secant squared plus tangent squared. And unfortunately, secant squared plus tangent squared doesn't show up here in the Pythagorean identities, so I'm just going to take this one that says tangent squared is the same thing as secant squared minus 1. Because then I can write secant squared plus, and then instead of tangent squared, I'll write secant squared minus 1. And the times 1 thing out here kind of just went away. And I can put these together now, so we have 2 secant squared of x minus 1. And that's just a little bit simpler than it was up here, because at least we just have one trig function instead of 2. So this one made use of factoring as kind of a trick, and also the Pythagorean identities. Number 6 is kind of an obvious one, because we have sine of pi over 2 minus theta, and that shows up exactly in one of our identities. This is a cofunction identity, so sine of pi over 2 minus theta is the same thing as just cosine of theta. And on bottom, cosine of pi over 2 minus theta is just sine of theta. And then cosine over sine can be simplified into just cotangent of theta. So this problem used cofunction and quotient identities. Moving right along to number 7, we have secant squared minus 1, and that's the same thing as tangent squared, so I'll put that on top, but we still have this over sine squared. I'm going to try and take this farther because we currently have 2 trig functions, and we might be able to combine this together into just one trig function. So I'm going to take the tangent squared from the top of that fraction, and then instead of dividing by sine squared, I'm going to think of this as multiplying by 1 over sine squared. Because you could also think of tangent as sine over cosine, so in this case sine squared over cosine squared. And then when we multiply that by 1 over sine squared, these just cancel out, so I'm left with just 1 over cosine squared. And of course that can be simplified farther because 1 over cosine is the same thing as secant. So we used a Pythagorean identity right away. Then this is just a little bit of algebra, and then this was a quotient identity, changing tangent into sine over cosine. And then after these canceled, we changed 1 over cosine back into secant, and that is a reciprocal identity. With number 8, I'm going to change secant into 1 over cosine, and then I'm going to work with this fraction here. So I'll keep sine from the top, but then instead of dividing by tangent, I'll write that as multiplying by 1 over tangent of x. And then I have to work with this fraction. So I'm going to take the sine from the top, and then instead of dividing by tangent, I'm going to multiply by 1 over tangent of x. Alright, so I could combine these because sine over cosine is just tangent, and now all of a sudden I have tangent of x times 1 over tangent of x. So if you just put this 1 over 1, these would just cancel, and I'm just left with 1 again. So this problem made use of reciprocal identities right away in the beginning, and then a quotient identity changing sine over cosine into tangent. In number 9, we have cosine of pi over 2 minus theta, which is a cofunction identity. I can change that into sine of theta, and then still times secant of theta. So I'll leave the sine of theta alone, but we can change secant into 1 over cosine, and that helps me a little bit because I can change sine over cosine into tangent of theta. So this problem made use of cofunction, reciprocal, and quotient identities in that order. With example number 10, it's not immediately obvious what to do. I guess we have cosine squared on top, which I remember is the same thing as 1 minus sine squared. So I suppose we could do this, and then we have this over 1 minus sine on bottom. But you have to be really careful here, because you can't just cancel the 1s and cancel these and say that you're just left with like minus sine or something like that. Because 1 minus sine is a factor all by itself. It can't be split up. But on top, if we have 1 minus sine squared, that is technically a difference of squares. I could factor that into 1 minus sine of theta times 1 plus sine of theta. And that's still over 1 minus sine of theta. And that's helpful because now I can cancel these entire factors, because it's like the entire thing in parentheses that I'm canceling out all at once. So that leaves me with just 1 plus sine of theta. And it's not squared, so I can't change it into cosine squared or anything like that. And I can't just change this into cosine either. Okay, so this is actually as simplified as I can get. So here we used the Pythagorean identities and then some factoring. But I want to show you another way of doing this problem, because there's another technique that can come in handy a lot of times, and that's multiplying by the conjugate of the denominator. So remember, the conjugate is basically, it's like the same factor, but the sign in the middle changes. So 1 minus sine of theta would become 1 plus sine of theta. So I'll do that on top and bottom of this fraction. And that makes this fraction just 1. So multiplying by this doesn't really do anything, it's just going to make it look different. So I'm going to leave the top alone. I'm not actually going to distribute the cosine squared in. But on bottom, I will FOIL these together, because when you do that with conjugates, you get a difference of squares. And that's because we have opposite signs here, so when you FOIL them together, the outer and the inner terms are going to cancel out. So I'm left with just 1 minus sine squared of theta. And that is actually cosine squared. And that, of course, is super helpful because now we can cancel out the cosine squareds, and we're left with just 1 plus sine of theta, just like we were in the first approach. So this approach took a little bit more work, but multiplying by the conjugate of the denominator is a really helpful technique, so I just wanted you to see that. In number 11, we've got sine squared and then minus sine squared times cosine squared, so two separate terms that are being subtracted. And I see a bunch of squared functions, so we'll probably be using Pythagorean identities, but nothing matches up with what we currently have. I noticed that both terms have a sine squared though, so I'm going to factor that out front. And if I do that, the first term would just leave me with a 1, and then the second term, well, this would cancel out, and I'm left with just cosine squared. And 1 minus cosine squared is a Pythagorean identity. So we have sine squared here, and then 1 minus cosine squared is sine squared again. So sine squared times itself would just be sine to the fourth of x. So this problem used a greatest common factor and a Pythagorean identity. Let's do the same thing for number 12. We've got cosine squared in both of these terms. So if I factor that out front, I'd be left with 1 plus tangent squared. And 1 plus tangent squared is the same thing as secant squared. So I can change this into cosine squared of x times secant squared of x. And cosine and secant are reciprocals, and when you multiply reciprocals together, you get 1. In other words, I'll just leave this cosine squared alone and change secant into 1 over cosine squared of x. And now you'll see that if I just put this over 1, the cosines cancel, and like I said, I'm just left with 1. This next set of 3 problems is going to require a lot of factoring. In number 13, we actually have 4 terms that we have to factor, and hopefully that clues you into using like factor by grouping, or I actually do it with a box. So first of all, think of this as x cubed minus x squared plus x minus 1. If you were factoring that with a box, it's convenient because you have 4 terms and 4 boxes that you have to fill in. So every term just goes in its own box, and then you just factor out of the box what you can. So out of this first column, we could take an x out. Here we could take a negative 1. In this first row, we could take out an x squared. And in the bottom row, pretty much nothing in common, just 1. So this would give me x squared plus 1 times x minus 1. But remember, the problem wasn't just x's, we had cotangent of x. So you can just change the x's back into cotangent of x's. So cotangent squared of x plus 1 times cotangent of x minus 1. And cotangent squared plus 1 is actually the same thing as cosecant squared. So it might make it a little bit simpler if I change this to cosecant squared of x, still times cotangent of x minus 1. And sometimes it's hard to tell when to stop simplifying these, but I think this is about as good as we can get, because if you try to take this farther, you could change cosecant into 1 over sine, and cotangent into cosine over sine, but if you multiply these together, nothing cancels out. It actually just gets worse because we have sine cubed on bottom. So I would just leave the problem where it's at. Number 14 gives us tangent cubed of x plus 1, and we don't have any identities that deal with tangent cubed, so somehow we have to change that into maybe like a tangent squared. And this is a sum of cubes, so we could try factoring it as a sum of cubes. So you'll want to remember your sum and difference of cubes patterns, which I'll leave here for just a second. So in this case, we'll factor it into tangent of x plus 1 as the first factor, and then the second one is tangent squared of x, and then minus tangent of x, and then plus 1. In the second factor, if you take the tangent squared and the plus 1 at the end and put them together, tangent squared plus 1 is secant squared. So I guess we could get this, but I don't think that taking this any farther will help. Again, tangent is sine over cosine, and secant is 1 over cosine. And multiplying these together wouldn't help anything to cancel out. With number 15, we'll try to factor this again. We have sine to the fourth minus 2 sine squared of x plus 1. And if you thought of this as x to the fourth minus 2x squared plus 1, you could factor that into, let's see, x squared and x squared. And then I just need 2 things that multiply to 1 and add to negative 2. So that'll just be negative 1 and negative 1. And then actually these factor farther because they're both difference of squares. So I'd have x minus 1 times x plus 1, and x minus 1 times x plus 1 again. So you could simplify this a little bit because we have 2 of these x minus 1 factors. So if you just write them as x minus 1 squared, that makes it a little bit easier. and then same thing with the x plus 1s. But remember, I replaced sine of x with an x, so we have to go back and do that at the end. So this would be sine of x minus 1 squared, and then sine of x plus 1 squared. So in these last two examples, the answer doesn't necessarily seem much simpler than it started with in the beginning of the problem, but the fact that we have it in factored form does help us. A lot of times factoring things helps us to find the zeros or solutions of equations, so it is nice to have them in factored form. Alright, we're getting close to the end here. In number 16 we have 1 over 1 plus cosine plus 1 over 1 minus cosine. So two different fractions with different denominators. And if we're going to add them together, we need common denominators. So the first fraction needs a 1 minus cosine of x on top and bottom, and the second one needs a 1 plus cosine of x. And lucky for us that these denominators are conjugates of each other. So we have 1 minus cosine of x on top, but then on bottom, again, multiplying these conjugates together gives us a difference of squares. So we have 1 minus cosine squared of x. In the second fraction, we would have 1 plus cosine on top, but the same difference of squares on bottom, 1 minus cosine squared of x. And now these have common denominators, so we can add the fractions together. So looking at the numerators, let's see what we have to add. We've got a 1 and another 1, so that would make 2. But here we've got negative cosine of x plus cosine, and those would cancel out. So we just have 2 over 1 minus cosine squared of x. But actually 1 minus cosine squared is sine squared. So this is the same thing as 2 over sine squared of x. And if you think about breaking this fraction apart, you could bring the 2 out front, and then you'd have times 1 over sine squared. So this is just 2 times cosecant squared of x. So whenever possible, try to not answer in fraction form, just change it into the reciprocal if you can. Number 17 is going to have us do the same thing. We're going to add two fractions together, so we're going to get common denominators. So the first fraction needed a cosine on top and bottom, and that would give me cosine squared on top. And on bottom, I'm just going to leave it how it is for now. Later we'll see if I want to distribute this in or not. And over here we have 1 plus sine as the same factor times itself. So again, I'm not going to FOIL those together. I'm just going to leave it as 1 plus sine of x squared. So it seems like we kind of have a mess here, but now that we have the same denominators, we can look at adding the numerators together. And as they sit, I can't really add anything together because this 1 plus sine is stuck being squared in parentheses. So I guess I will actually FOIL these together. So I didn't write the workout, but foiling that together would give me 1 plus 2 sine of x plus sine squared of x. And it seems like we just made it worse, but we do have cosine squared of x plus sine squared of x, and if I put those together, they just make 1. So all of a sudden, these two are just 1 plus another 1, that would make 2. So now I have 2 plus 2 sine of x, and I just combine them into one fraction over the same denominator, cosine times 1 plus sine. Now this is about as far as we can go, but if you look at 2 plus 2 sine of x and 1 plus sine of x, those two factors look really similar. This one's just twice as big. Actually, I could factor a 2 out, and that would give me 2 times 1 plus sine of x, and now I can cancel this factor with the 1 plus sine of x on bottom. So now I just have 2 over cosine of x, and just like we did in the other problem, I can think of that as 2 times 1 over cosine of x, because 1 over cosine is secant, so this is just 2 times the secant of x. So after all of that, after having these two different fractions with different denominators, getting common denominators, changing these into a Pythagorean identity, sine squared plus cosine squared, and making this huge mess with all these fractions, it all simplifies down to 2 secant of x. Alright, we're on to our last two examples. In 18 we have sine squared over 1 minus cosine of x, and the directions say to rewrite the expression so it's not in fractional form. So the first idea I have is to multiply by the conjugate of the denominator, because that worked pretty well for us before. So I'm going to leave the top alone. I'll just leave it as sine squared of x times 1 plus cosine of x. But on bottom, I'm going to multiply these two together because, again, conjugates give us a difference of squares. So this would be 1 minus cosine squared of x. And 1 minus cosine squared is sine squared. So I'll keep the top the same, but I'll change the bottom into sine squared of x, because now I can cancel these two, and I'm left with just 1 plus cosine of x. And of course that's not in fractional form anymore. Let's try the same thing for 19. So the conjugate of this bottom factor would be secant plus tangent. So on top we'd have 3 times the secant of x plus the tangent of x. Again, I'm going to leave that factored apart. But on bottom I will multiply these together because these conjugates will give me a difference of squares, which would be secant squared of x minus tangent squared of x. and secant squared minus tangent squared is just 1. And that works out really nice because I could change this to just being 1, and dividing by 1 doesn't really mean anything. So I can just basically cancel that out, and I'm left with 3 times secant of x plus tangent of x. And at first I was wondering if we could put these together into just one trig function, but if you think of secant as 1 over cosine of x and tangent as sine of x over cosine of x, I suppose we could try to put these together because we have common denominators, but this is putting it back into fractional form, so we're kind of getting away from what the directions were asking us to do. So I'll just leave it how it is, and don't even worry about distributing the 3 and just leave it factored apart. So 3 times secant of x plus tangent of x.